From the moment of the Big Bang to the elusive nature of dark matter, the universe holds secrets so profound they defy our most advanced science. These mysteries aren't just cosmic curiosities. They shape the fate of galaxies, the flow of time, and the very fabric of existence. In this journey through the universe's greatest enigmas, we'll confront the frontiers of human knowledge and the haunting silence that still surrounds them. Look up on a clear night. What do you see? A tapestry of stars, planets, maybe a streaking satellite. It looks full, even crowded, but this is an illusion, an astonishing one. The truth is this: more than 99.99% of the universe is empty, almost nothing, a cosmic void. So here's the question: why? Why is the universe, with all its galaxies, stars, and planets, mostly empty space? It's a question that has haunted us for thousands of years. It has sparked revolutions in physics. And it leads to some of the most mind-bending truths we've ever discovered. In 1915, Albert Einstein, working alone in the middle of a world at war, proposed something radical. Space and time are not static. They bend, they stretch, they respond to mass and energy. This was general relativity. It told us that space isn't a container, it's a fabric. Put a heavy object, like a star, on it, and the fabric curves. Other things roll toward it. Gravity, Einstein said, isn't a force, it's geometry. Now, picture this. If space is a fabric, what lies between the threads? Einstein's equations hinted at something odd. If you removed all the stars, all the galaxies, space would still exist. But not flat and quiet. It could expand. Like dough rising in the oven, space itself could stretch, even without anything in it. And in 1929, an astronomer named Edwin Hubble proved it. Hubble looked at distant galaxies and saw something shocking. They were all moving away. The farther they were, the faster they fled. The universe, he realized, was expanding. Not because things were moving through space, but because space itself was growing. It meant that the empty space between galaxies wasn't just vast, it was getting bigger. The nothing was swelling, and the more it grew, the emptier the universe became. But there's a deeper mystery. Atoms, the building blocks of you, me, everything, are mostly empty space too. Imagine an atom scaled up to the size of a football stadium. The nucleus, where nearly all the mass is, would be a marble at the center. The electrons would be tiny specks buzzing around the nosebleed seats. In between, nothing. Matter itself is almost nothing. So here's the twist. The universe is empty not just between things. The things themselves are mostly empty. And then came quantum field theory. This is where physics went full science fiction. According to this theory, space is not truly empty. Even in the deepest vacuum, tiny particles flicker in and out of existence. Virtual particles, ghosts of matter, pop, gone. This quantum foam roils beneath the silence, an ocean of nothingness that teems with almost somethings. It also gave rise to an idea so wild it was initially rejected: dark energy. In the late 1990s, two rival teams of astronomers measured distant supernovae. Their goal was to determine how fast the universe was slowing down. Instead, they found it was speeding up. Something was pushing galaxies apart faster and faster, a repulsive force, not matter, not even dark matter. They called it dark energy, and it was everywhere. This force, lurking in empty space, made up nearly 70% of the universe. So most of the universe isn't just empty. It's filled with something that acts like nothing but with power, a strange pressure from the vacuum itself. Once scientists realized that dark energy dominates the universe, they began to ask a question: what will happen to everything else? If this expansion continues, galaxies will drift beyond each other's reach. Stars will burn out. Black holes will evaporate. Eventually, only cold, thin radiation will remain. A universe of darkness, of silence, of emptiness. This idea is called the heat death of the universe, a time when all usable energy is gone. No stars, no warmth, no change, just an ocean of space, and yet there's beauty in this bleak vision. Because to get here, we had to understand the very fabric of reality. We had to map the invisible, listen to starlight, and invent mathematics that dances with the infinite. We had to look at the darkness and say, what's there? So why is the universe mostly empty? Because it has to be. Because emptiness is not failure, it is the stage. Without empty space, there could be no movement, no time, no life. The void is what allows light to travel, atoms to bond, galaxies to spin. Emptiness is not nothing, it is possibility. In the silence between stars, we find our greatest questions, and sometimes our greatest answers. The universe, vast and quiet, whispers its secrets to those who dare to listen. Somewhere out there, beyond the stars, beyond the galaxies spinning in silent grace, is a boundary. A place we cannot see past, a cosmic curtain. Here's the question. What lies beyond the edge of the observable universe? The observable universe is a sphere around us, roughly 93 billion light-years across. That's the furthest light has had time to reach us since the Big Bang, given the age of the universe and the constant expansion of space. But that's only what we can see. So what's past that? More stars, more space, nothingness, another universe? The answers are as wild as science gets. And getting there, to the edge of what we can know, is a journey packed with mystery, failure, wonder, and revelation. The idea of an edge to the universe seems simple, even childlike, but to scientists, it's a minefield of paradoxes. In the early 20th century, astronomers like Edwin Hubble discovered that the universe was expanding. This expansion meant that some parts of the cosmos were slipping out of reach. Imagine blowing up a balloon with dots on it. As the balloon grows, the dots move away from each other. But unlike a balloon, space itself stretches. So distant galaxies aren't moving through space, they're being carried away with space. It's not that the galaxies are moving fast. It's that space between us and them is growing. This leads to something strange. Some light, even if it was emitted billions of years ago, will never reach us because space expands faster than the light can travel. The boundary formed by this limit is called the cosmic light horizon. Beyond it lies the unobservable. Scientists can map the observable universe. We see galaxies, microwave background radiation, and the early afterglow of the Big Bang. But what lies beyond that sphere? Can we ever know? Here's where things get surreal. Some theories suggest the universe is infinite, that beyond our horizon lies more universe, just like the patch we can see, stretching endlessly. If true, it means there are more galaxies out there than grains of sand on Earth. Maybe even regions of space identical to our own by sheer statistical chance. But inflation theory offers an even stranger possibility. Proposed by Alan Guth in the 1980s, inflation suggests that in the first trillionth of a second after the Big Bang, the universe expanded faster than the speed of light. This smoothed out space, explaining why distant regions of the universe look so similar. Inflation implies that what we see is just a bubble in a much larger multiverse. Each bubble may have its own laws of physics, gravity might be stronger, or time might flow differently. We live in one bubble. Beyond our bubble are others. Some could be unimaginably strange. Some might harbor life. Others might be sterile or collapse moments after birth. But here's the tension. If we can't see beyond our observable universe, how can we test any of this? This is where theory meets the frontier of human understanding. Scientists build models, run simulations, and study the cosmic microwave background for subtle clues. Tiny ripples that might be fingerprints of inflation or collisions with other bubbles. There was a moment of near euphoria in 2014. The BICEP 2 experiment announced they had found evidence of gravitational waves from inflation. It was like hearing an echo from the birth of time. But soon, dust from our galaxy turned out to be the culprit. Science stumbled. But that's part of the journey. Every wrong turn sharpens the map. The edge of the observable universe isn't a wall. It's a limit of what we can currently perceive. Like standing in a fog, what lies beyond is hidden, not necessarily absent. In fact, the universe may not have an edge at all. General relativity allows space to be curved. If space is positively curved, it could loop back on itself like the surface of a sphere. You could travel in a straight line and end up where you started, never hitting an edge. Or space could be flat and infinite, as most current evidence suggests. Then the observable universe is just a drop in an endless cosmic ocean. And yet, for all our models and measurements, we are still bound by light and time. We are observers on a cosmic raft trying to map a shore we cannot reach. So what lies beyond the observable universe? Maybe more of the same, maybe something entirely different, maybe nothing at all. We don't know. But that not knowing is not a failure, it's a kind of freedom. Astronomer Carl Sagan once said, "Somewhere something incredible is waiting to be known." That spirit drives science forward. It drove the building of telescopes so powerful they can see galaxies as they were billions of years ago. It fuels missions to map the early universe in microwaves. It inspires equations scrawled on chalkboards, dreams woven into simulations, and stories told under stars. The edge of the observable universe is not an end. It is a beginning, a place where imagination, guided by reason, reaches as far as the light will go. Imagine an object so dense, so powerful, that not even light can escape its grasp. A place where the known laws of physics break down and time itself may cease to exist. This is the black hole, a cosmic enigma that has both fascinated and perplexed scientists for over a century. The term black hole was coined in the 1960s, but the concept dates back to the 18th century. Jean Michel and Pierre-Simon Laplace speculated about dark stars with gravitational pulls so strong that light could not escape. It wasn't until Einstein's theory of general relativity in 1915 that the modern understanding of black holes began to take shape. Yet even Einstein was skeptical of their existence, considering them mathematical curiosities rather than physical realities. So how did these theoretical constructs become one of the most studied and mysterious objects in the universe? The journey from skepticism to acceptance is a tale of human curiosity, perseverance, and the relentless pursuit of knowledge. In the early 20th century, Karl Schwarzschild provided the first exact solution to Einstein's equations. He described a point of infinite density known as a singularity, surrounded by an event horizon, the point of no return. Despite this breakthrough, the idea of black holes remained controversial. It wasn't until the 1960s and 70s that observational evidence began to mount. Astronomers detected X-ray emissions from binary star systems, suggesting the presence of invisible, massive companions, likely black holes. The discovery of quasars, extremely luminous and distant objects powered by supermassive black holes, further solidified their existence. One of the most compelling pieces of evidence came from the study of the center of our own galaxy. Andrea Ghez and her team at UCLA used advanced telescopes to track the orbits of stars near the Milky Way's core. Their observations revealed a massive, invisible object, Sagittarius A star, with a mass equivalent to 4 million suns. For decades, black holes were invisible, detectable only through their effects on surrounding matter. That changed in April 2019, when the Event Horizon Telescope collaboration released the first ever image of a black hole's event horizon. This monumental achievement captured the shadow of the supermassive black hole at the center of galaxy M87, located 55 million light-years away. The image, resembling a glowing ring of fire, was the result of years of collaboration among scientists worldwide. One notable contributor was Dr. Katie Booman, who developed an algorithm crucial for processing the vast amounts of data collected by the EHT. This visual confirmation of a black hole's existence was more than a scientific milestone. It was a testament to human ingenuity and our unyielding desire to understand the universe's most profound mysteries. Despite these advancements, black holes continue to challenge our understanding of physics. One of the most perplexing issues is the information paradox. According to quantum mechanics, information cannot be destroyed. However, when matter falls into a black hole, it seems to vanish, leading to a conflict between quantum theory and general relativity. In the 1970s, Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, suggesting they could eventually evaporate over time. This raised further questions about the fate of the information consumed by black holes. Recent theoretical developments, such as the concept of islands in spacetime, offer potential resolutions, but the debate remains unresolved. Moreover, The discovery of primordial black holes, hypothetical remnants from the early universe, could provide insights into the nature of dark matter, one of cosmology's greatest mysteries. If these ancient black holes exist, they might account for a significant portion of the universe's unseen mass. Black holes, once relegated to the realm of theoretical speculation, have become central to our understanding of the cosmos. They challenge our perceptions of space, time, and reality itself. Each discovery brings new questions, pushing the boundaries of science and philosophy. As we continue to explore these cosmic enigmas, we are reminded of the words of physicist Kip Thorne. Black holes are where God divided by zero. They represent the limits of our knowledge and the infinite possibilities that lie beyond. The darkness of the black hole is not a void, but a canvas upon which we project our curiosity, imagination, and the enduring human spirit. What happens when everything ends? Not just you, not just Earth, not just the sun, but everything. The stars, the galaxies, the very fabric of space and time. Will the universe collapse into itself in a fiery implosion? Will it be torn apart, atom by atom, in a cosmic tantrum? Or will it simply fade, growing cold and dark until there's nothing left to see, nothing left to feel? This isn't science fiction, it's science, and scientists have been chasing this mystery for over a century. It started with a mistake. In 1917, Albert Einstein added a strange term to his equations. He called it the cosmological constant, a kind of anti-gravity designed to hold the universe still. Back then, scientists believed the universe was static, eternal, unchanging. Einstein's equations said otherwise. They suggested the universe should be expanding or contracting. But that didn't make sense, so he fudged the math. Then came Edwin Hubble. In the 1920s, Hubble used the most powerful telescope of his time to peer into the sky. He noticed something strange. Distant galaxies were drifting away, not just moving, but speeding away faster the farther they were. The universe was expanding. Einstein called his cosmological constant the biggest blunder of his life. But it wouldn't be the last time the cosmos would surprise us. As decades passed, astronomers refined their tools. They launched satellites, measured cosmic background radiation, and studied the distribution of galaxies. By the 1990s, two teams of scientists set out to measure how fast the universe was slowing down. They expected to find that gravity was putting the brakes on expansion. Instead, they found the opposite. The universe was speeding up. Some mysterious force, was pushing space apart faster and faster. They called it dark energy. No one knew what it was. Still don't. It makes up nearly 70% of the universe, and it acts like a kind of reverse gravity. Instead of pulling things together, it pushes them apart. This changed everything. With dark energy in the mix, scientists had to rethink the universe's fate. They proposed three possible endings, three cosmic finales. One of these is the Big Crunch. Imagine the universe as a balloon. At first it inflates. Galaxies move away from each other, but if there's enough matter, enough gravity, it eventually stops expanding. Then it starts to shrink. Galaxies rush back together, stars collide, temperatures rise. Everything collapses into a dense, hot point, back where it all began. The Big Crunch is the poetic ending, a full circle. But current measurements suggest there's not enough matter to pull it off. The universe isn't slowing. It's accelerating, so scientists considered another scenario. Next one is the Big Rip theory. What if dark energy gets stronger over time? Imagine space expanding so violently that galaxies can't hold together, then solar systems, then planets, then atoms. The force becomes so intense it tears everything apart, literally. One by one, cosmic structures unravel, stars are ripped open, matter dissolves. Eventually, even space and time break down. The universe ends in shreds. It sounds like horror, but it's only a theory. For now. The third possibility is quieter. Another one, heat death. This is the most widely accepted scenario. In this version, the universe keeps expanding. Galaxies drift so far apart they disappear from each other's view. Stars burn out, black holes evaporate, even atoms decay. Everything spreads thinner and thinner, cooler and cooler, until all that's left is a cold, dark, empty expanse. No light, no life, no motion, just silence forever. These aren't just numbers on a chalkboard. Behind every equation there are people, dreamers, strugglers. In the late 1990s, the discovery of the accelerating universe came from two rival teams. They raced to measure distant supernovae, exploding stars that acted like cosmic mile markers. They worked tirelessly, sleep-deprived, doubt-ridden. When both teams came to the same shocking conclusion, it shook the foundations of cosmology. Einstein's blunder might have been right after all. Others, who studied the rotation of galaxies, pointed to the existence of dark matter decades earlier, another invisible force shaping our universe. Their stories are filled with setbacks, miscalculations, skepticism, but also awe, wonder, and the thrill of unlocking something vast and eternal. So how does it end? No one knows for sure. The Big Crunch looks unlikely. The Big Rip is possible, but needs more evidence. Heat death. That seems the most probable. A universe that fades into stillness. But maybe that's not the point. Maybe the beauty lies not in the end, but in our journey to understand it. We are tiny, fragile, flickers in cosmic time, yet we ask the biggest questions. We build machines to peer across billions of light years. We listen to the echoes of the Big Bang. We write equations that stretch across the sky. In facing the end of the universe, we see our own impermanence, but also our curiosity, our courage, our endless hunger to know. And in that, perhaps, there is something eternal. Something that doesn't fade, not light, not matter, but wonder. And maybe, just maybe, that's enough. What if everything we know is just one version of reality? Imagine somewhere in a parallel universe, another you is reading this same sentence. But maybe they're doing it upside down, or while riding a dragon, or maybe they never existed at all. The idea seems ripped from the pages of science fiction, but it isn't. It's a real question that modern physics dares to ask. Is our universe just one of many? This isn't just speculation. It's rooted in theories that emerged from the deepest inquiries into space, time, and the nature of existence itself. It's a story that begins in the heart of a cosmic mystery and stretches to the very edge of what science can currently understand. A story of equations, telescopes, dreams, and the people bold enough to follow them. In the 1960s, scientists were basking in the triumph of the Big Bang Theory. The universe, they discovered, had a beginning. And like forensic detectives, they could trace the cosmic clues back to a moment 13.8 billion years ago. Light from that primal fireball, the cosmic microwave background still glows faintly across the sky. The universe had a birth, but the theory raised more questions than it answered. Why, for instance, is the universe so flat? Why does it look the same in every direction? And why did it produce the perfect conditions for stars, planets, and life? In the 1980s, physicist Alan Guth proposed a bold solution: inflation. Not economic inflation, but cosmic inflation, a period of ultra-fast expansion in the tiniest sliver of a second after the Big Bang. According to Guth, the universe didn't just expand, it exploded outward at a speed that made light seem sluggish. Inflation solved many puzzles. It explained the universe's uniformity and flatness, but it came with a strange twist. The equation showed that inflation never really stops. It might slow down in some regions, forming bubble universes like ours. But in others, it continues endlessly, spawning new universes like foam in a never-ending sea. This was the beginning of the multiverse hypothesis. Each bubble universe could have different laws of physics. In one, gravity might be stronger. In another, time might run backward. Most would be barren, hostile. But a few, like ours, could be just right for life. This idea was radical. Yet it wasn't just theoretical hand-waving. It emerged naturally from the mathematics of inflationary cosmology, and it aligned with another strange puzzle. At the heart of everything lies quantum mechanics, the theory that governs the smallest particles in the universe. It's weird, it's wild, and it's real. In the quantum world, particles don't have fixed positions. They exist in clouds of probabilities. Only when observed do they choose a state. This bizarre behavior led to one of the most mind-bending interpretations of quantum mechanics, the many worlds interpretation. The idea was simple but shocking. Every time a quantum event happens with multiple outcomes, the universe splits. One universe for each possible result. You flip a coin. In one universe, it's heads, in another, tails. Quantum computing, entanglement, and new experiments lent weight to the idea that reality might be far less singular than we think. So now, two streams converge: inflationary cosmology and quantum mechanics. Both suggest the same thing. There may be more universes, not metaphorically, literally. This is not just a story about equations, it's about people. Alan Guth, wrestling with cosmological puzzles late at night, scrawling equations on napkins. Hugh Everett, a young man with a radical idea, watching his theory get ignored. Max Tegmark, MIT physicist, categorizing multiverse types with the precision of a librarian arranging infinite bookshelves. Andre Linde, who took Guth's ideas further, visualizing a bubbling cosmos with each bubble a universe while sipping tea in a Moscow apartment under surveillance during the Cold War. These scientists faced ridicule, isolation, even depression, but they kept asking the big questions. Because wonder drove them. Because the mystery mattered, and they aren't alone. The search for the multiverse isn't just for physicists. Philosophers wrestle with its implications. Artists imagine its landscapes. Science fiction writers explore its possibilities. We all hunger to understand what might lie beyond the veil. So is the multiverse real? We don't know. We may never know. Some versions are forever beyond our reach. Others might leave subtle fingerprints in the cosmic microwave background, in the behavior of particles, in the statistical quirks of the cosmos. Scientists are hunting for these signs, with satellites, with colliders, with math. Even if proof remains elusive, the idea has already reshaped how we think about reality. It humbles us, it stirs awe, it reminds us that our universe, vast as it is, may be just a ripple in an infinite ocean. And it whispers something beautiful, that every moment matters, that somewhere, perhaps, every choice plays out, that reality is richer than we can possibly imagine. In one universe, you never read this essay, but in this one, you did. And maybe, just maybe, that means something. It's a moment frozen in the history of the universe, the formation of a supermassive black hole. Picture the heart of a galaxy, an invisible force so powerful that it distorts light itself. Its gravity is a hungry predator, pulling in anything that strays too close. Stars, gas, even entire worlds vanish into it as if swallowed by an abyss. But how do these giants form? Where do they come from? And why do they exist? For years, astronomers have been staring into the vast star-filled void, trying to answer these questions. The answer, it turns out, is not just a matter of numbers or equations. It's a story of curiosity, discovery, and the unexpected twists and turns of science. The year was 1915, and Albert Einstein had just completed one of the most revolutionary works in physics, the theory of general relativity. One of the strange predictions of this theory was the existence of black holes, regions of space where gravity was so intense that nothing, not even light, could escape. At the time, no one could truly understand their significance, nor could they fathom how such objects could form. Fast forward to the late 1960s, when astronomers first observed something mysterious at the centers of distant galaxies. They saw an eerie, energetic glow, a brilliant light produced by material being dragged into something invisible. They didn't know it then, but this would mark the birth of a new era in cosmic discovery, the age of supermassive black holes. The size of these objects was staggering. Supermassive black holes can be millions, even billions of times more massive than our sun. Yet their event horizons, the boundary beyond which not even light can escape, are often only a few times the size of our solar system. How could such monstrous forces arise in the seemingly quiet hearts of galaxies? It wasn't until the 1970s that scientists realized something even stranger. These black holes seem to be linked to the structure and evolution of galaxies themselves. Larger galaxies, like our Milky Way, appeared to have supermassive black holes lurking at their centers. But smaller galaxies? They didn't seem to have them. The connection between these cosmic giants and the galaxies they inhabited raised a burning question. How do these supermassive black holes form? To answer that question, astronomers began to look deeper into the mysteries of the cosmos. One of the earliest breakthroughs came from a daring observation in 1963, when the American astronomer Martin Schmidt discovered the first quasar. Quasars are extremely bright, distant objects that are powered by the intense radiation emitted as material falls into a supermassive black hole. Imagine this. Gas and dust spiral toward the black hole, heating up as it accelerates, until it reaches temperatures so high that it emits enormous amounts of light. This radiant glow became a signal for astronomers that something extraordinary was at play. But how could these quasars exist if the black holes at their centers were still a mystery? In the 1980s and 1990s, a group of scientists, including Roger Penrose and Kip Thorne, began to refine the theories about the formation of black holes. Penrose's work on the singularity at the center of a black hole suggested that the immense gravitational forces would continue to grow over time, trapping more and more material. But how would this initial collapse occur? How did it go from a simple star to a supermassive beast? At the same time, scientists like Reinhard Genzel and Andrea Ghez were using a new tool to solve this cosmic puzzle. High-resolution telescopes that allowed them to peer deep into the heart of our own galaxy, the Milky Way. They observed stars orbiting a seemingly invisible object at the center of the galaxy, an object with a mass millions of times that of the Sun. In 2020, they were awarded the Nobel Prize in Physics for their work, providing concrete evidence that a supermassive black hole, named Sagittarius A*, resides at the center of our galaxy. The discoveries piled up. It became clear that these black holes weren't just theoretical curiosities. They were real. But the question of how they formed was still wide open. Some scientists proposed that they grew from the collapse of massive stars, while others suggested that they were the result of the merging of smaller black holes. Perhaps they had formed in the chaotic conditions of the early universe. The key to answering the riddle of black hole formation may lie in the early universe itself. As the universe expanded after the Big Bang, it cooled down and matter began to clump together. Over time, vast clouds of gas and dust would condense under the force of gravity, leading to the formation of stars. But the story of supermassive black holes is a little different. Some scientists believe that in the early universe, there were fluctuations in the density of matter. These fluctuations might have caused massive clouds of gas to collapse directly into black holes, bypassing the star formation stage entirely. This process, called direct collapse, could explain how the first supermassive black holes formed so quickly after the Big Bang. If this theory is correct, then these black holes could have grown rapidly, accumulating vast amounts of matter and energy, eventually becoming the titanic objects we observe today. But the formation of supermassive black holes isn't just a theoretical puzzle. There's a practical challenge too. How could a black hole grow so massive in the relatively short time it took for galaxies to form? After all, the universe's first stars began to appear only a few 100 million years after the Big Bang, and galaxies began to form shortly after. Supermassive black holes must have had an incredibly fast and efficient way of gobbling up gas and dust. The solution may lie in the idea of galactic mergers. As galaxies collide and merge, the supermassive black holes at their centers could eventually combine into a single, even more massive black hole. These mergers release enormous amounts of energy as gravitational waves ripple across spacetime. This process could explain the enormous sizes of the supermassive black holes we see today. As astronomers continue to probe the deepest reaches of space, they're slowly unraveling the mysteries of these cosmic giants. Today, powerful telescopes like the Event Horizon Telescope are helping scientists directly observe the shadow of a black hole. In 2019, it made history by capturing the first ever image of a black hole, located at the center of the galaxy M87. That image, a faint glowing ring of light surrounding an inky black core, was a watershed moment for science. It confirmed what many had long suspected, that supermassive black holes are real, that they shape galaxies, and that they are at the very heart of some of the most mysterious phenomena in the universe. Yet, even with all the advances in observational technology, there are still many unanswered questions. How do these black holes affect their host galaxies? Do they play a role in star formation, or do they simply consume everything in their path? In many ways, the journey into the heart of the universe is just beginning. Supermassive black holes may seem like distant, abstract objects, but they are intricately woven into the fabric of the universe. They are not just destroyers, they are also creators. They shape the galaxies in which they reside, influencing star formation, galaxy evolution, and even the growth of large-scale cosmic structures. Perhaps the most profound insight that comes from studying these enigmatic giants is the realization that the universe is far stranger and more beautiful than we can fully comprehend. Supermassive black holes are both a symbol of the power and mystery of the cosmos and a reminder of how much we still have to learn. It's not just the science that matters, it's the sense of wonder and curiosity that drives us to explore the unknown. Whether it's the light from a distant quasar, the shadows of a black hole, or the faint whisper of gravitational waves, every discovery brings us one step closer to understanding the grand story of the universe and our place within it. And so the journey continues. In 1950, a simple, almost offhand comment made by the physicist Enrico Fermi during a lunch break at Los Alamos National Laboratory sparked one of the most enduring and perplexing mysteries in modern science. "Where is everybody?" Fermi asked. The question was born from a curious observation. If the universe is so vast and potentially teeming with life, why haven't we found any evidence of extraterrestrial civilizations? Why is the cosmos so silent? This simple question, known today as the Fermi paradox, has haunted us for decades. The paradox is both a question and a challenge. Given the vastness of the universe, billions of stars, planets, and galaxies, why do we have no definitive proof of intelligent extraterrestrial life? If life is common, as many expect, why has contact eluded us? The story of the Fermi paradox is not just about science. It's about curiosity, mystery, and the search for answers to one of humanity's most profound questions. Are we alone in the universe? Imagine standing on a hill in the middle of nowhere, gazing up at the night sky. The stars twinkle like distant diamonds, each one potentially hosting planets of its own. This sight is a window into the cosmos, a reminder of just how vast the universe truly is. The Milky Way, our galaxy, contains over 100 billion stars, and there are at least 100 billion other galaxies scattered across the observable universe. Within this vast expanse, scientists have discovered that planets are common, with thousands of exoplanets, planets orbiting stars beyond our Sun, identified by the Kepler Space Telescope alone. Given these numbers, the chances of finding other planets that could support life seem almost certain. The famous equation formulated by astronomer Frank Drake, known as the Drake equation, attempts to quantify this probability. It takes into account factors like the rate of star formation, the number of stars with planets, the fraction of planets that could support life, and the lifespan of technologically advanced civilizations. According to the equation, there could be millions of technologically advanced civilizations in our galaxy alone. So, if the numbers are so favorable, why haven't we detected any signals, seen any visitors, or found any definitive proof of extraterrestrial intelligence? For decades, astronomers have been trying to answer this question. The search for extraterrestrial life has taken many forms. The most famous of these is the search for extraterrestrial intelligence, aka SETI, which listens for radio signals from distant stars in the hope that one of these signals might be from an intelligent alien civilization. But despite decades of scanning the heavens, SETI has found nothing. One of the first challenges scientists faced in trying to answer the Fermi paradox was the sheer scale of the universe. The distances between stars are mind-boggling. Even the closest star system to us, Alpha Centauri, is over 4 light-years away, and our current space probes would take thousands of years to reach it. This enormous scale means that even if there are civilizations out there, we may be too far away to detect them with current technology. Another challenge is the nature of the signals we're looking for. In the 1960s, the famous astronomer Frank Drake, alongside other scientists, launched the first attempt to listen for extraterrestrial signals. They used radio telescopes to search for any signs of alien transmissions. But even if there are alien civilizations out there, they might not be using the same methods of communication as us. They might not use radio waves at all, or their signals might be undetectable to our instruments. Despite these setbacks, there have been intriguing discoveries along the way. In 1977, a scientist named Jerry Amon detected a mysterious signal from deep space known as the WOW signal. The signal was a strong burst of radio waves, unlike anything expected from known cosmic sources. It lasted for 72 seconds, and despite repeated efforts to find it again, no similar signals have been detected. The WOW signal remains one of the most tantalizing pieces of evidence for extraterrestrial communication, yet it remains unexplained. In the 21st century, the search expanded with the discovery of exoplanets. The Kepler Space Telescope has revealed thousands of planets orbiting other stars, many of them in the habitable zone, the region around a star where conditions might be right for life to develop. This discovery has fueled hopes that life might be common across the universe. But even with all these planets, the question remains, why haven't we heard from anyone? The search for extraterrestrial life has reached a dramatic turning point. The tools we've developed, space telescopes, radio observatories, and advanced computer models, are more powerful than ever. Yet, despite all this, we remain in silence. The paradox grows. If intelligent civilizations are likely to exist, why haven't they contacted us? One theory suggests that perhaps alien civilizations are out there, but they are choosing to remain silent. Known as the zoo hypothesis, this idea proposes that advanced extraterrestrial civilizations are aware of us but are deliberately avoiding contact, much like humans might avoid interacting with animals in a zoo. These civilizations could be waiting for humanity to reach a certain level of technological maturity before making themselves known. Perhaps they are following some kind of cosmic non-interference principle, akin to the Prime Directive in Star Trek, which prohibits interference with less advanced civilizations. Another possibility is that advanced civilizations are short-lived. This idea, known as the Great Filter, proposes that intelligent civilizations may inevitably destroy themselves before they can develop the means to explore the stars. The Great Filter could be something inherent in the development of life itself. Perhaps the transition from simple life to complex life, or from non-technological to technological civilizations, is exceedingly rare. In this case, the Fermi paradox may not be a mystery at all. The silence could simply be the result of a cosmic cemetery filled with the ruins of once great civilizations that failed to survive long enough to make contact. The Fermi paradox also raises another possibility. Perhaps we are truly alone. Perhaps Earth is the only planet in the entire universe where life has evolved to an advanced, intelligent form. The vastness of the universe, rather than being a guarantee of alien life, may be the reason we haven't found anyone. Life may be so rare that the chances of two civilizations crossing paths are vanishingly small. This idea is known as the rare Earth hypothesis, which argues that Earth's conditions may be incredibly rare, even among the vast number of planets in the universe. The Fermi paradox is not just a scientific mystery, it's also a mirror that reflects our deepest fears and desires. The silence of the universe can feel lonely and isolating. It raises profound questions about humanity's place in the cosmos. Are we truly unique? Are we the only ones who have ever looked up at the stars and wondered what lies beyond? Or, as the paradox suggests, is the universe filled with civilizations that have simply passed us by, leaving us to wonder why? The paradox has also prompted a new kind of thinking. If intelligent civilizations are out there, perhaps we need to redefine what we mean by communication. After all, the vastness of space and the limitations of our current technology might mean that we are simply not looking in the right way or at the right time. Scientists are now exploring new methods of detecting alien life, from studying the chemical composition of distant exoplanets' atmospheres for signs of life, to searching for technosignatures, artificial signals that might be generated by alien technologies. Moreover, recent advancements in the search for extraterrestrial intelligence have brought us closer to solving the paradox. In 2021, the discovery of fast radio bursts, brief, powerful bursts of energy from deep space, has added a new layer to the mystery. Are these natural phenomena, or could they be the result of alien technology? These bursts could hold the key to understanding not just the nature of the universe, but also the potential existence of alien civilizations. The Fermi paradox may not have a definitive answer yet, but it has spurred humanity to look deeper into the cosmos than ever before. Whether we are alone or surrounded by intelligent life, the search for answers is an adventure that defines our species. The paradox challenges us to confront our assumptions about the universe and to expand our horizons in ways we never thought possible. For now, we continue to look up, listening for the faintest of signals, wondering if we're the first, the only, or simply the most recent. The universe is vast and full of secrets, some of which we may never fully understand. But the search itself is what drives us, and in that search we find meaning, wonder, and perhaps one day an answer to the question that Fermi first posed so many years ago: where is everybody? Most of the universe is made of something we can't see, not can't see with the naked eye. And yet, without it, nothing would exist. This is dark matter, we know it's there. Galaxies spin too fast to be held together by the visible matter alone. Light bends around invisible masses. The early universe shows patterns shaped by something we can't detect, something huge. But we don't know what it is. It began, as many great scientific stories do, with a puzzle. In the 1930s, a Swiss astronomer was studying the Coma cluster, a group of galaxies swirling around one another. He measured their speeds and compared them to the visible mass of the galaxies. They were moving too fast. According to the laws of gravity, they should have flown apart. But they didn't. He suggested there was something else, some invisible glue holding them together. He called it dark matter. His idea was met with skepticism. For decades, the scientific world mostly ignored it. People thought maybe he got the numbers wrong. In the 1970s, astronomers studied spiral galaxies. They expected to find stars rotating more slowly as you moved outward from the center, like planets in our solar system. Instead, they found something shocking. The stars on the outskirts were moving just as fast as those near the center. That shouldn't happen unless there was more mass than we could see. Something massive, invisible, wrapping the galaxies like a cosmic halo. But now, the evidence was undeniable. Still, no one knew what dark matter actually was, and we still don't. The discovery of dark matter's influence sparked a race. If it made up most of the universe's mass, and it did, around 85% of it, then what was it? Scientists proposed candidates, WIMPs called weakly interacting massive particles. Theoretical particles that barely touch regular matter, axions, ultralight particles born from strange quantum symmetries, sterile neutrinos, cousins of known particles that don't interact via the usual forces. Detectors were built deep underground, shielded from cosmic rays, cold as space. Waiting for a faint nudge, in Italian mountains, in South Dakota mines, in Canadian labs. Years passed, then decades. No confirmed detection. Telescopes searched the skies. They mapped galaxy clusters, gravitational lensing, the cosmic microwave background. Everything pointed to dark matter's gravitational pull. But the particle itself, still missing, it became one of the biggest mysteries in physics. And tensions rose. What if we were wrong? What if dark matter wasn't a particle at all? Some physicists suggested tweaking gravity itself, changing the equations rather than inventing a new substance. Modified Newtonian dynamics. Controversial, hotly debated, still debated. Meanwhile, some teams thought they caught glimpses. Tiny blips, anomalies, hints. Always disappearing on retest. It was like chasing a ghost through a mirror. In the midst of frustration, new approaches bloomed. Astrophysicists began to use the universe itself as a laboratory. By mapping how galaxies clump together over billions of years, they traced the skeleton of dark matter. Simulations, like the Millennium Simulation and Illustris, recreated the cosmos with virtual dark matter scaffolds. These models matched reality stunningly well. They showed how dark matter shaped everything. Without it, galaxies wouldn't form, stars wouldn't coalesce, life wouldn't arise. Dark matter is the silent architect of the universe, and yet it doesn't shine, it doesn't speak. It's the ultimate background character, holding up the whole show. Meanwhile, new technologies emerged. Space telescopes will soon scan the sky with unprecedented precision. Maybe they'll catch the shadow. Or maybe we need to think differently. Physicists like Lisa Randall explored dark sectors. What if dark matter isn't one thing, but a whole hidden world? Particles with their own forces, maybe even their own chemistry, entire shadow universes whispering beside ours? Science fiction? Maybe. Or maybe just science not yet understood. Dark matter is a reminder that the universe is not built to satisfy our intuition, that sometimes the most important parts are invisible. And that wonder lives not just in what we know, but in what we don't. Vera Rubin once said, "We have peered into a new world and have seen that it is more mysterious and more complex than we had imagined." The search continues in labs and telescopes and equations. Maybe dark matter will reveal itself tomorrow. Maybe not for another 100 years, but the journey has already transformed us. It's taught us humility, patience, creativity, and a kind of reverence, for the universe is not only stranger than we think. It's stranger than we can think, and in that strangeness we find not despair, but awe. We are small, but we are curious, and we are reaching into the dark. Imagine you own a map of everything made of matter, stars, planets, gas, dust, you, me. Now imagine half of that matter is missing, not just misplaced, gone, vanished. Where is the missing baryonic matter? We're not talking about dark matter. This is ordinary matter. The kind made of protons, neutrons, electrons, the kind we can, in theory, detect. Yet somehow, when we add up all the visible stuff in the universe, we fall short, way short. Nearly half the baryons predicted by our best theories just aren't where we expected them to be. This isn't just a bookkeeping error, it's a cosmic cold case. And solving it would take decades, a cast of persistent scientists, and the sharpest instruments in space. The story starts with the Big Bang. In the first moments of creation, the universe cooked up the ingredients for everything: hydrogen, helium, a dash of lithium. Based on how the universe expanded and cooled, we can calculate with high precision how many baryons it should have made. Cosmic microwave background radiation, the afterglow of the Big Bang, gives us a snapshot of those early moments. Satellites have mapped this radiation in stunning detail, and from that, we can estimate the amount of baryonic matter in the universe. The number is solid. But when astronomers began to look at galaxies, stars, and gas clouds, the stuff that baryons typically form, they found less than half of what should be there. It was as if the universe had misplaced billions of solar masses worth of normal matter. Some hoped the missing baryons were hiding in galaxies. in stars too faint to see, or in clouds of cold gas too diffuse to detect. But surveys of galaxies came up short. Others looked at galaxy clusters, where hot gas glows in X-rays. These clusters accounted for some of the missing matter, but not all. No matter where we looked, something didn't add up. It was as if the universe had swallowed half its own contents. The key to cracking the case came from a shift in thinking. What if the missing baryons weren't hidden in galaxies? What if they were in between galaxies, in the vast, quiet stretches of intergalactic space? Astronomers began to suspect that the baryons might exist as diffuse, hot gas stretched across filaments of the cosmic web. This idea wasn't new, but it was hard to prove. This form of matter, called the warm-hot intergalactic medium, is incredibly hard to see. It doesn't glow like stars, it doesn't block light like dust, it doesn't shine invisible light at all. It's thin, it's hot, and it's invisible to most telescopes. Detecting the WIM would require a different approach, a clever one. Enter the quasar. Quasars are distant galaxies with bright, active centers powered by black holes. They shine across billions of light years, and when their light passes through clouds of gas, some of that light is absorbed. Each kind of atom leaves a specific fingerprint, a dip in the spectrum, a telltale sign. If WIM gas lies between us and a quasar, it might leave behind faint absorption lines, especially in X-ray or ultraviolet wavelengths. Teams of scientists began to use the Hubble Space Telescope and Chandra X-ray Observatory to search for these signs. It took years, and then, slowly, they started to find them. The missing baryons weren't gone. They were hiding in plain sight, spread thinly across the cosmic web. Heated to millions of degrees, too faint to see directly but leaving whispers in the light of distant quasars. In 2018, a major breakthrough came. Using the combined power of space telescopes, 2 independent teams detected these filaments of hot gas between galaxies. They found enough missing matter to solve the puzzle. After decades, the numbers finally added up. The discovery of the WIM changed more than just a few numbers. It revealed how the universe evolves. We now understand that galaxies don't just sit quietly, they breathe. They exchange matter with the intergalactic medium. Galactic winds blow hot gas out, gravity pulls new material in. The WIM is both the furnace and the freezer of galaxy growth. Studying this medium gives us a better grasp of star formation, black hole feedback, and the life cycle of galaxies. It also highlights the persistence of science. For decades, researchers like Michael Schull, Charles Danforth, Fabrizio Nicastro, and others chased shadows. They worked on uncertain margins, instruments pushed to their limits, data just at the edge of detection. They faced skeptics, null results, funding challenges, but they kept going. Science is rarely fast, often it's frustrating, but in the end, the payoff is huge. The mystery of the missing baryons is, in many ways, a story about trust. Trust in the math, trust in the data, trust in the long arc of investigation. It reminds us that the universe is not built to be obvious. It hides its truths in the spaces between. The WIM is still being studied. We have much to learn about its structure, temperature, and role in cosmic evolution. But we found it. By looking not at the stars but between them, the case of the missing baryons shows that even in a universe filled with brilliant light, sometimes the biggest revelations lie in the faintest signals. And maybe that's true for us too. Sometimes understanding comes not from what stands out, but from what quietly holds everything together. Not the stars, but the space between them. What if everything, every galaxy, every atom, every whisper of time began from a single silent point? What if all the stars and planets and even the space between them were once packed into a dot smaller than an atom? And what if that dot exploded? Not into something, but into everything. This is the story of the Big Bang. But it's not just the beginning of the universe. It's a human story, a story of doubt, imagination, failure, and wonder. A story that starts in darkness. For most of history, we thought the universe had always existed. The stars were eternal, the sky unchanging, Even Einstein believed the universe was static. When his equations told him otherwise, that space should be expanding or contracting, he added a cosmological constant to cancel it out. He fudged the math. Then in the 1920s, something incredible happened. A Belgian priest and physicist named Georges Lemaitre proposed a radical idea. What if the universe was expanding? What if it all started from a primeval atom? His idea was ignored. Meanwhile, in California, Edwin Hubble used a powerful telescope to measure distant galaxies. What he found changed everything. The galaxies weren't just moving. They were speeding away from us. The farther they were, the faster they were fleeing. Space itself was stretching. The universe was expanding. Lemaitre was right. And Einstein called his earlier correction the biggest blunder of my life. But what does an expanding universe imply? Run the clock backward and everything shrinks. Galaxies get closer, stars merge, atoms compress, until you reach a point where space and time themselves break down. A moment of beginning, the Big Bang. Still, many resisted the idea. It sounded too much like a creation myth. Even the name Big Bang was meant as a joke, coined by British astronomer Fred Hoyle, who favored a different model. He imagined a universe with no beginning. In 1964, two young radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, were trying to tune their radio antenna. They kept picking up a strange noise, a faint, persistent hiss that wouldn't go away. They cleaned the antenna, removed nesting pigeons, checked every possible source. Still, the hiss remained. Unbeknownst to them, just 40 miles away, a team at Princeton was preparing to search for that exact signal. The afterglow of the Big Bang, the radiation left over from a universe born in fire. The teams connected, and the hiss became history. Penzias and Wilson had discovered the cosmic microwave background, a fossil of light from 380,000 years after the Big Bang. This light had been traveling for billions of years, stretched by the expanding universe into microwave frequencies. It was the smoking gun. The Big Bang was no longer theory, it was observation. With the CMB as a guide, scientists began to reconstruct the early universe. The first moments were unimaginably hot and dense, a fireball of particles and light. As it expanded, it cooled. Quarks formed protons and neutrons, later atoms. Then light could finally move freely, creating the CMB. Small ripples in that light, tiny fluctuations, eventually became galaxies, stars, and planets. We mapped the CMB in greater detail with satellites like COBE, WMAP, and Planck. Each mission brought sharper images, and every pixel of those images told a story. Of gravity tugging on matter, of dark matter shaping galaxies, of dark energy speeding up the expansion. We learned the universe is 13.8 billion years old. We saw its baby picture. Yet questions remained. What sparked the Big Bang? What came before? Was there a before? Some scientists proposed inflation, a tiny fraction of a second when the universe expanded faster than light, smoothing out the wrinkles. Others explore quantum gravity, multiverses, cyclical models. We stand on the edge of understanding, and we peer into the dark. The Big Bang isn't just a theory. It's a triumph of human curiosity. It's the product of minds that refused to accept what seemed obvious, that looked beyond the stars and asked, why is there something rather than nothing? It's a story of people like Lemaitre, quietly bold, like Hubble scanning the skies, like Penzias and Wilson, puzzled by a hiss that turned out to be the voice of creation. We are still unraveling this story, still debating, still discovering. And in doing so, we learn not just about the universe, but about ourselves, that we can imagine the unimaginable, that we can trace our origins in light, that from a single point of infinite potential, everything, including wonder, can unfold. And maybe that's the most beautiful thing of all. The universe didn't just begin with a bang, it began with possibility. And that possibility continues in every star, in every question, in you. What if everything we know, our galaxy, our stars, our solar system, our very planet, is being pulled towards something we can't see? something vast, mysterious, hidden behind a curtain of cosmic dust and stars. What is it? A monster? A black hole? A cluster of galaxies? Or is it something we don't understand at all? Scientists call it the Great Attractor, and it's pulling us in. It began with a drift. In the 1970s and 80s, astronomers noticed something strange about the Milky Way and its neighboring galaxies. They weren't just moving through space, they were streaming. Thousands of galaxies, including ours, were flowing in the same direction. Not slowly, not gently, fast, at over 1 million miles per hour. But why? Gravity only works when there's mass. And this motion suggested something massive was pulling on the local universe. But when scientists looked in the direction of the motion, they saw nothing much. Nothing that could explain this gravitational tug. The region was blocked by the plane of the Milky Way, a thick, dusty zone known as the zone of avoidance. It's the blind spot in our cosmic vision. And behind it, something was pulling the entire Laniakea supercluster, our galactic neighborhood, toward it. The term Great Attractor was born, but no one knew what it was. To solve the mystery, astronomers had to get creative. They used infrared telescopes, which can see through dust. They turned to radio waves, which pierce even the thickest galactic fog. Bit by bit, they began to map the hidden structures behind the Milky Way. What they found astonished them. There was something there. A massive region of densely packed galaxies, clusters upon clusters, forming an enormous gravitational basin. At its heart, the Norma cluster. It alone contains thousands of galaxies and weighs millions of billions of times more than the Sun. This was a big piece of the puzzle, but it wasn't the whole answer. Because even beyond the Great Attractor, galaxies kept moving, as if something even bigger was pulling from farther away. Enter the Shapley supercluster. Located over 650 million light-years from Earth, it is one of the most massive structures in the known universe. Some scientists now believe the Shapley supercluster is influencing the flow we once attributed to the Great Attractor. In other words, the Great Attractor might not be a single object. It might be a symptom. A local signpost on a much longer road, a ripple in a river flowing toward a deeper ocean. As more of the universe became visible through new instruments, satellites like IRES, telescopes like Parkes and Arecibo, and now surveys like 2, MASS, and GALEX, we began to map the cosmic web in all directions. We discovered that our galaxy isn't just one among many. It's part of a vast interconnected structure, filaments of galaxies woven like a spiderweb across space. The Laniakea supercluster, to which we belong, stretches over 500 million light-years and contains more than 100,000 galaxies, and we are moving within it, drawn along invisible threads pulled by gravity. Toward what? That's still a question. The Great Attractor is no longer a single mystery. It's a doorway. It opened our eyes to the vast gravitational currents of the universe, to motion on unimaginable scales, to the idea that our galaxy is not stationary. We are in motion, always. The Great Attractor might never be a single satisfying answer. It might not be a thing in the way we first imagined, but in chasing it, we discovered a deeper truth. That space is not empty, that galaxies are not scattered at random, that there are flows, rivers of gravity, tides of motion, and we are part of them. The story of the Great Attractor is the story of our journey into cosmic humility. It reminds us that we are small, that we are not the center, that we are being carried on currents we barely understand, but also that we can see it, we can map it, name it, chase it. We can feel the pull of something vast and unseen, and choose to follow, because science isn't just about answers, it's about the thrill of the question, of being pulled toward knowledge the way galaxies are pulled across the universe, of never standing still. We are being carried, together, toward something bigger. What if a galaxy had no stars? After all, what is a galaxy if not a glittering collection of stars, millions, even billions, dancing together in space? But in 2018, astronomers announced something strange, something that shook the foundations of what we thought we knew. They had found a galaxy that seemed to be missing its stars. No glow, no shimmer. Just a faint ghost, a wisp of a galaxy floating in the dark. It was called NGC 1052 DF2, and it was about to challenge everything. The story begins with the Dragonfly telephoto array, a set of lenses more like a camera than a telescope. Developed by Peter Van Dokkum and Roberto Abraham, the Dragonfly was designed to find the faintest objects in the sky. Not the bright stars or flashy quasars, but the shadows, the leftovers, the things other telescopes missed. In 2014, the Dragonfly team started discovering ultra-diffuse galaxies, big galaxies, but extremely faint, like someone had taken a normal galaxy and turned down the brightness until it was barely visible. Then came NGC 1052 DF2. It was enormous, roughly the size of the Milky Way, but with 1/200th of the stars. You could fly right through it and barely notice. Even stranger, it had almost no dark matter. This was a shock. Dark matter is supposed to be the glue that holds galaxies together. It makes up most of the mass in the universe. Without it, galaxies shouldn't form. They shouldn't survive. But NGC 1052 DF2 didn't seem to care. It was there, drifting silently, defying gravity and expectation. Van Dokkum and his team studied the motions of star clusters within the galaxy. These clusters acted like test particles. Their speeds revealed the galaxy's mass. And the math didn't lie. The stars were moving slowly, much too slowly to be orbiting around a massive dark matter halo. In fact, the galaxy seemed to have no dark matter at all. The implications were seismic. First, it proved that galaxies could exist without dark matter. This went against decades of understanding. It meant dark matter might not be as essential as we thought, at least not always. Second, it gave new support to the dark matter model itself. Why? Because if dark matter didn't exist, if gravity just worked differently, then all galaxies should behave in that different way. But NGC 1052 DF2 wasn't behaving like other galaxies. It wasn't acting like it had dark matter, which meant other galaxies were. In a strange way, the absence of dark matter in one place confirmed its presence in others. Of course, the discovery sparked debate. Some scientists questioned the measurements. Maybe the galaxy was closer than we thought. Maybe the mass had been underestimated. But Van Dokkum doubled down. In 2019, his team found a second galaxy, NGC 1052 DF4, with similar properties. Lightning had struck twice. The mystery deepened. So how do you make a galaxy without dark matter? Several theories emerged. One idea, tidal stripping. Imagine two galaxies colliding and one gets torn apart. Its dark matter is pulled away. Its stars scattered. What's left is a faint remnant, a ghost. Another theory, failed galaxies, clouds of gas that never formed stars. They never had enough gravity to ignite. But these didn't quite explain NGC 1052 DF2. It had some stars, just very few. It had star clusters. Globular clusters, dense balls of ancient stars usually found in massive galaxies. This galaxy had them too, but not the galaxy around them. It was like finding skyscrapers in the middle of a desert. Some scientists suggested that these galaxies formed in special environments. Near larger galaxies like NGC 1052, maybe they were born in the chaos of galactic mergers. Or maybe, and this is where the wonder creeps in, we simply don't know. Maybe the universe still has tricks we haven't seen. The mystery of starless galaxies isn't solved, but that's the point. NGC 1052 DF2 didn't just give us answers. It gave us new questions. It reminded us that science isn't a book of facts. It's a story, always being written. Sometimes the most powerful discoveries come not from what we see, but from what we don't. The missing stars, the missing matter, the whisper in the void. These galaxies are cosmic punctuation marks. Pauses that make us listen. And in that listening, we grow. We sharpen our tools, reframe our theories, reach further. We stop assuming, and we start wondering. Because in the end, a galaxy without stars reminds us of something profound. That even in darkness there is structure, that even in silence there is motion, and that sometimes the universe teaches not by what it shows, but by what it hides. What happens when the laws of physics break? Not bend, not stretch, but snap. There's a place where space and time twist so hard they tear. A place where gravity is infinite, size is zero, and logic itself frays. That place is a singularity. You find it at the center of black holes. You find it, maybe, at the very beginning of the universe. And if you fall into one, no one can tell you what happens next. In 1915, Albert Einstein published his theory of general relativity. It was elegant, it was strange, and it was right. It showed that gravity wasn't a force, it was geometry. Mass bends space and time, and that bending tells matter how to move. But buried in Einstein's equations were monsters. Singularities, points where curvature becomes infinite, where equations yield nonsense. At first, many scientists thought singularities were just artifacts, mathematical quirks, not real things. Then, in 1939, J. Robert Oppenheimer and Hartland Snyder did the unthinkable. They imagined what would happen if a massive star collapsed under its own weight. Their conclusion, it would keep collapsing, forever. No force could stop it, not light, not pressure. Not even the laws of physics. It would form a black hole, and at its core, a singularity. Still, the idea remained fringe. Even Einstein doubted black holes were real. Then, in the 1960s, a young physicist named Roger Penrose changed everything. Using rigorous math, Penrose proved that singularities aren't just possible. They're inevitable. If you compress matter enough, you must get one. Stephen Hawking extended this work to the entire universe. He proposed that the Big Bang itself began as a singularity. It was no longer a curiosity, it was our origin and maybe our end. So what is a singularity? A singularity is where our understanding collapses. It's a point of zero volume and infinite density. A place where time and space are so distorted they lose meaning. Imagine a trampoline. Put a bowling ball on it and it sags. That's gravity. Now imagine a weight so heavy it punches a hole straight through the fabric. That's a singularity. Near it, space is curved, time slows, tides stretch your body. This is known as spaghettification, a real term, a grim one. Radiation near the singularity behaves strangely too. Photons, particles of light, get trapped. Time becomes directionless. The laws of thermodynamics start to break down. Matter loses identity. Atoms can't hold together. Particles get crushed into oblivion. This is where classical physics ends, and quantum physics tries to take over. But here's the catch. General relativity and quantum mechanics don't get along. One describes the large, one the small. Singularities demand both, and so far no one has found the bridge. Physicists are desperate for a theory of quantum gravity, a single framework that unites Einstein with quantum mechanics. String theory is one candidate. It imagines particles not as points but as vibrating strings. At high energies, near a singularity, the strings might smooth out the infinities. Loop quantum gravity is another. It suggests space-time is made of discrete loops like a woven fabric. At the singularity, the fabric might bounce. Instead of a beginning, we'd have a rebound. A big bounce instead of a big bang. But none of these theories are proven. And no telescope can see inside a singularity, so scientists study the edges. The event horizon, the radiation that escapes, the way black holes spin. In 2019, the Event Horizon Telescope gave us the first image of a black hole's shadow. Not the singularity, but its fingerprint. And in Hawking's final years, he wrestled with the black hole information paradox. Does information get destroyed in a singularity? Quantum mechanics says no, but general relativity says yes. Resolving that conflict might unlock the secret. Singularities may lie forever beyond our reach. Or maybe in the math, in the radiation, in the echoes of the early universe, we will find the answer. But even now they teach us something profound. They show us where our knowledge ends. They remind us that nature does not care about our expectations. That truth may be stranger than logic, more beautiful than equations. They challenge us to go further, to think deeper, to imagine a world beyond what we can test. The behavior of matter near a singularity is not just a scientific question. It is a philosophical one. What happens when everything breaks? What remains when nothing makes sense? We may never touch a singularity, but in chasing it, we touch the edge of knowledge. And that may be the closest we ever come to understanding everything. You're doing it right now, moving through time. You can't see it, you can't touch it, you can't hold it still. But it never stops. It flows when you sleep, when you speak, when you breathe. And yet, no one really knows what time is. We can measure it, slice it into seconds, hours, centuries. But when we try to define it, really define it, we enter a maze. Is time a thing, a force, a dimension, an illusion? This is the story of how science has tried to answer that question. A story that stretches from ancient shadows to the edges of the universe. A story of clocks, black holes, broken hearts, and brilliant minds. Because to understand time is to understand everything. Time begins, as most human things do, with the sun. Ancient people watched shadows move and stars shift. They carved calendars into stone, tracked moons, built monuments like Stonehenge and the pyramids to catch the light at just the right moment. Time was sacred, cyclical, tied to seasons, crops, survival. Then came mechanical time. In the 14th century, clock towers tolled across Europe. Suddenly, time wasn't just for priests and astronomers. It was public, audible, quantifiable, tick-tock. The Industrial Revolution turned time into a machine. Trains ran on schedules. Workers punched clocks. Time zones sliced the earth. We didn't just live in time. We lived by it. But science still didn't know what time was. Then came Isaac Newton. In 1687, he gave us his laws of motion. Time to Newton was absolute. It ticked the same for everyone, everywhere. An invisible stage on which the universe played out. But Newton was wrong. He didn't know it yet, because waiting in the wings was Albert Einstein. In 1905, Einstein published his theory of special relativity, and time changed forever. Literally. Einstein showed that time is not fixed. It is relative. It stretches and compresses depending on how fast you move. Imagine two twins. One stays on Earth. The other rockets into space near the speed of light. When they reunite, the space traveler is younger. This isn't science fiction. It's been measured with atomic clocks on planes. And that's just the beginning. In 1915, Einstein published General Relativity. He showed that gravity bends time. Clocks tick slower in stronger gravity. Stand on a mountain, and time moves faster for you than it does at sea level. Drop a clock near a black hole, and it nearly stops. This idea isn't just theoretical. GPS satellites orbiting Earth have to adjust for time dilation caused by both speed and gravity. Without accounting for Einstein, your directions would be wrong by miles. Time, it turns out, is woven into the fabric of space. It's the fourth dimension. We live in space-time, but Einstein's universe has a strange consequence. It doesn't require the present. Past, present, future, they all exist, all equally real. To Einstein, time is a landscape. We don't flow through it, we are in it, all at once. It's our perception that moves. Still, we feel time passing. We remember the past, we anticipate the future, we age, we lose, we grow. So where does the arrow of time come from? Why do we remember yesterday but not tomorrow? The answer lies in entropy. Entropy is disorder, the tendency of things to go from ordered to messy. A cup shatters, smoke disperses, ice melts, and the universe, born in an orderly Big Bang, is moving toward greater entropy. That's why we remember the past, because it was more ordered. That's why eggs don't unbreak. Entropy gives time a direction, but this too is being questioned. Quantum mechanics, the theory of the very small, doesn't care about time direction. Its equations work the same forward and backward. And some physicists think time might be an emergent property, not fundamental. Something that arises only in systems with many interacting parts, like temperature, like consciousness. Could it be that time only exists inside the universe, not outside it? Could it be that the Big Bang didn't start time, but emerged from timelessness? Today, physicists continue to chase time. Some study black holes where time nearly halts. Others look to the early universe where time may have been something else entirely. There are theories with multiple times, theories with no time, theories where time is a loop. But through it all, one thing remains. Time touches everything. It governs stars and sand grains, dreams and decay. It shapes our stories. We measure our lives in time, in birthdays, in anniversaries, in first words, in final breaths. Time is loss. Time is love. And even if science one day reveals that time is not fundamental, even if it's just a trick of entropy or a shadow of deeper laws, we will still feel it. We will still tell stories like this one, with beginnings, middles, and ends. Because we are creatures of time, moving forward, asking questions, building meaning, tick-tock,